Hi. In this video, we're going to go over section 4.2, which is about types of energy. So energy, as we talked about, is given the definition of the ability to do work. But it's a little bit easier to think about it as, the capacity to cause change, whether that be through the motion of something or the location of something. All of those would count as forms of energy or as situations or objects containing energy. And there are lots of different ways that we can express this. And each of them details a unique mechanism of change. So, in today's lecture, we're going to talk about a bunch of different types of energy and why it's beneficial for us to differentiate them from one another. So, there's going to be a lot of vocabulary words. We're going to get to know mechanical energy, potential energy, kinetic energy, gravitational potential energy, spring potential energy, and thermal energy. Okay. So we'll start in right away with kinetic energy. So you may be familiar with that KIN as a prefix for a word, and that's really describing motion, right? That KIN. So if we wanted to write a description of this, we would say that kinetic energy is the energy of motion. If an object is moving, right, its location is changing. And so since, we talked about the fact that energy's capacity to cause change, then that would certainly count. Now, the symbol that we use for this is a capital K. So anytime we see a capital K around, we know we're talking about kinetic energy. And we can calculate how many joules of kinetic energy we have. And the way we do that is we look at a force versus displacement graph. And we, in the last section, talked about the fact that if you look at the area of a force versus displacement graph, you're going to find the energy being stored in the object. So when we think about moving, we require a net force in order to move. So this particular graph is going to be a net force versus displacement graph in order to get that, achieve that motion. And if we find the area of this graph, we will find the kinetic energy. So this area is just a box, so we can just do base times height. So we would do net force times delta x. And we're going to try to simplify that a little bit. In Newton's second law, we know that F net is the same as ma. So we could write this area as ma delta x. And this A and delta X, those are both kinematics terms. And so if we actually rearrange our V squared equals V naught squared plus 2A delta X, if we actually assume that we start at an initial velocity of 0, we can replace this A delta X with 1/2 V squared. And that is how we would commonly see the equation for kinetic energy. Is a slight variation on that is written as 1/2 mv squared. So kinetic energy, the amount of it that we have depends on two things, right? We know it depends on the mass of the object. If the object is bigger and it's moving, we would expect it has more energy. And then also how fast it's moving, right? So if an object is moving faster, we would expect that it would have more kinetic energy. All right. Let's talk about gravitational potential energy. So what are we describing when we say that something has gravitational potential energy? Well, what we're saying is we're saying like, hey, by holding something up into the air, we give it the potential to cause change. Okay, so if we think about anything that's in free fall, it was up high over a surface, and through that height, we released it and it sped up. Okay, so that location seems to have some kind of energy associated with it. And that's different from just having an object that is on a surface. So if it's on a table or it's on the ground already, we could be holding onto an object as it is on that surface. And if we let go, nothing may happen. No change may occur. So we would say that there is not any energy associated with that particular location, right? So this gravitational potential energy is really trying to describe the energy of location and the fact that being above a surface can cause change when being on a surface really doesn't. The symbol that we use for this is a capital U sub G. So the capital U refers to potential energy and the sub G refers specifically to gravitational energy. And the equation that we can use that will allow us to calculate how many joules of gravitational potential energy we have, it, much like the rest of these equations, comes from a force versus displacement graph. So the force in this case is going to be the force of gravity, right? Because the force of gravity is what pulls things down to the earth. And the displacement that we're undergoing is a displacement in the y direction, right? It's some kind of height. And if we were to take some measurements of the force of gravity at different heights, we would find that the graph would look something like this. And so if we are able to calculate this area, then we will calculate the gravitational potential energy. And again, this is just a box, so we can just do base times height, Fg times delta y. And we know that to calculate the force of gravity, we need to do mg. So it is much more common that we write this equation as mg delta y. And on the equation sheet, they actually add a little delta in front of the ug as well, because in order to utilize this gravitational potential energy, we do have to end up moving. Okay, let's talk about spring potential energy. This one is a little bit more familiar to us because we talked about it so much in 4.1. So spring potential energy, you may also hear it called elastic potential energy. Both of those terms refer to the same thing and they are used interchangeably. In fact, the College Board pretty much 50-50 calls it spring or elastic potential energy. But what they're trying to describe here is the energy that comes from deformation. So for a spring, for example, you stretch the spring and the spring can spontaneously go back to its original shape. And so when we deform it, we put energy into that spring and the energy gets released again when it goes back to its original shape. Now the reason why some people call it elastic potential energy is because it's not limited to springs. It could be a rubber band, right? A rubber band will spontaneously go back to its original shape. It could be one of these fun little children's toys that we just call poppers, where we can deform the popper and flip it inside out, and then it is able to spontaneously, well, maybe with a little bit of help, return to its original shape. And the fun thing about these is you can drop them and it causes the shape to return to its original shape and they go flying up into the air. We do demos about that in class. So if something can spontaneously return to its original shape, then when it is deformed, we say that it has spring potential energy inside of it. And the symbol that we use is U sub S. Again, U for potential energy, S specifically for spring. And the equation that we have comes from the spring force versus stretch graph. And we are familiar with what that graph looks like from the previous lecture. Okay, so this one looks a little bit different. It is a triangle area that gets formed rather than a rectangular area that gets formed. But regardless, this area will give us that spring potential energy. So since it is a triangle, we're going to use the area of triangle formula, which is 1/2 base times height. So 1/2 times spring force times the stretch. And we also remember from Hooke's law that spring force can be calculated by doing kx. So it is simplest to calculate the energy stored in a spring by doing 1/2 kx squared. Now, there is an assumption that's being made here, okay? So this assumes, this assumes that the initial stretch or the initial displacement of the spring is 0. Okay, so we're assuming an ideal spring here where we are stretching it from its unstretched state. So if we instead have a stretched spring and we ask how much more energy do I add by stretching it more, we would have to do a little bit more math than just using 1/2 kx squared. All right. The last energy that we are going to have an equation for is thermal energy. Well, this isn't really the absolute last energy that you could come into contact with. There's chemical energy, there's electric energy, there's a bunch of other ones, but they just don't qualify as mechanics. And this is a mechanics class. So we are not going to delve into a study of chemical energy or of electric energy. But thermal energy, okay, so thermal energy is the energy of heat or light or sound. Okay. So you can take your hands, this is a really easy one to do, right? Take your hands, put them together, rub them like it's cold outside and you're trying to warm up, and your hands become warm. And that's because you are generating heat. Okay, so you are generating some energy in your hands by rubbing them together. And specifically, the thing that's doing that is the force of friction. So force of friction is going to be part of our equation. So this symbol is U therm, and that's kind of like a home-brewed symbol. That's really just the symbol I use in order to be specific about thermal energy. Sometimes you might just see it written as W. W is for work. That's going to be our topic of 4.3. That's often what we may see it written as. Okay, and we can calculate this thermal energy really in a very specific situation. It's really the energy that is being dedicated to thermal due to friction. So if we took some data of how much friction force there is as we move a certain distance, then we would find that the graph would look something like this. And this area is going to give us our thermal energy. And so since this is a rectangle, we can just do base times height, FF times D. Now, the thing I would like for you to know is that D means distance. Okay, not displacement, it's the distance that you go. Mostly because this force of friction is a non-conservative force. We'll talk about what it means for things to be non-conservative forces in a future lecture. All right, so these equations are all hugely important, so much so that I'm going to put all of them into a red box because these are the tools that we will use in order to figure out how many joules of energy a particular object has. 3 of them are on the equation sheet. And it is the first three. So kinetic energy, gravitational potential energy, and spring potential energy are all present on the equation sheet. Sadly, thermal energy is not. If you want to substitute thermal energy as for work, then there is the equation for work on the equation sheet, but not specifically for something like thermal energy. Okay. So with that, these are the things that we really need to think about when we think about what kind of energy does an object have or is present in a particular situation. We're really thinking about, is this moving? It has kinetic energy. Is it high above a surface? It has gravitational potential energy. Is it, can it be deformed and spontaneously come back together? Then it has spring energy. Is it dissipating energy to heat, light, or sound? Okay, then it's gonna have some thermal energy. Now, there is a broad category for some of these, and that broad category is mechanical energy. Okay, so mechanical energy is defined as energy due to the motion or position of an object. Okay, so what are we talking about then when we talk about mechanical energy? I'm going to use ME for mechanical energy. Again, that's kind of a home symbol, but it works really well. What we're talking about is we're talking about motion of an object. So we are talking about kinetic energy. We're talking about position of an object. So that could be gravitational potential energy. Or when they say position of an object, they also could mean position of, the ends of the object, meaning deformation of that object. So mechanical energy is just kind of like it's almost like a catch-all to refer to the combined kinetic, gravitational, and spring energies. And that's kind of leading us to how you can organize energy for yourself, because these are a lot of terms. And we want to make sure that we kind of understand what each of these terms is trying to really say to us. So if we have just energy, just as like one big category. Within that category of energy, we're going to see two subcategories, okay? And one of those subcategories is this mechanical energy. The other subcategory, at least for us in this class, is thermal. Okay, because thermal energy does not get included when we think about mechanical energy. Now, within mechanical energy itself, right, we have more subcategories. We have good old kinetic energy, energy of motion. We also have our potential energies. And there are two potential energies, right? There is, you gonna do it? Be a square. Okay, there we go. We got gravitational. And then also the other potential energy that we have is spring. Now, why do they get that extra word of potential in there? It's because they basically are an energy storage mechanism is how they're often considered, is energy storage. So you could have something high above the ground and there's energy associated with that, even if the object itself is not necessarily doing anything. Same thing with a spring, right? So we could deform an object, we could have energy in that object, but the object itself doesn't necessarily have to be doing anything. It doesn't have to be moving. And it could cause motion later. So that's why we add that word potential, because it's supposed to designate like the potential to cause change, the potential for things to start moving, for example. Okay, so that's kind of how energy is really organized within all of these different layers and all these different vocabulary words. But what I would like to end with today is us just doing a quick example problem. So what we have is we have a 78 kilogram skydiver who's got a speed of 62 meters per second at an altitude of 870 meters above the ground. So we kind of like took a snapshot of how this skydiver is moving at this particular moment in time. What we can do is we can determine the kinetic energy of the skydiver. So if we go up, we can find our kinetic energy equation. It's just 1/2 mv squared. And since we know that the skydiver is 78 kilograms and we know that the speed is 62 meters per second, then we can take out our calculator and get that the kinetic energy is 149,916 joules, right? It's a lot of joules of energy right there. Because this skydiver is also above the ground, right? That he's above the surface, we know that there also is some kind of potential energy associated with him. Specifically, it would be gravitational potential energy. The guy's not going to deform and come back to his original shape. So we're not going to worry about that spring potential energy. Instead, we're going to calculate just his gravitational potential energy. So what did we say he was? He was 78 kilograms times G times our delta Y. That is 870 meters above the ground. And yet again, if we just plug all that into our calculator, we get that this skydiver has 665,028 joules of gravitational potential energy. It's a lot. It's a lot of joules. And lastly, we can find out how much mechanical energy is possessed by this skydiver. Now we know mechanical energy is the combination of kinetic and gravitational and spring. So since we have 149,916 joules of kinetic energy, we have 665,028 joules of gravitational energy. We have 0 joules of spring energy. Then we can just add those together in order to figure out how much mechanical energy this skydiver has. And he has 814,944 joules of mechanical energy.